This is the fourth video in my series of videos on Georg Cantor's contributions to the founding of the theory of transfinite numbers. In this video I'm going to be making a start on the second article, so the 1897 article. As we've seen in the first article, it was kind of split into two parts. The first part concentrated mostly on cardinal numbers and their properties, and in the second half it concentrated on simply ordered aggregates and their properties. In this article we move on to a particular type of simply ordered aggregate called a well-ordered aggregate, and we're going to quickly be moving on to ordinal numbers, and that's ordinal numbers are going to be the main focus of this video and the rest of the videos that I make in this series. There is a slight change in style and feel from the first article to the second article. So in the first article the main focus was really definitions and concepts, so explaining the definitions and explaining the concepts. There were some theorems there, and a couple of big theorems at that. But in the second article, which I'm moving on to now, there's much more in the way of theorems. Obviously there are still definitions and concepts to be introduced and explained, but there's a lot more theorems. So regretfully I'm not going to be able to go through every single theorem and every single proof. So what I've tried to do is to select some of the more interesting or relevant theorems. In some cases I will actually go through a theorem and its proof in quite some detail. In other cases I'll just state the theorem, either by writing it on the board behind me or actually just reading it from the book and saying it out loud. In other cases I might just skip it altogether, skip the theorem altogether. If I go through a proof of a theorem and there is a reference to another theorem that I've not gone through, then I'll always make an effort really to state what that theorem says, so point you in the right direction so that you can refer to it yourselves if necessary. Okay, so let's get started on this second article. So let's have a look at the definition now of a well-ordered aggregate. So a simply ordered aggregate F is well ordered if its elements F, that's lowercase f, ascend in a definite succession from a lowest F1 such that there is in F an element F1 which is lowest in rank, and very importantly if F primed is any part of F, and if F has at least one element of higher rank than all elements of F primed, then there is an F primed of that's lowercase f primed of uppercase F, which follows immediately after uppercase f prime, so that no elements in rank between f primed, lowercase f primed and uppercase f primed occur in F. So just looking at this, putting these two together actually, if we say for example our aggregate F is equal to F1 and F sub 1. So this is the least element F1 that we're told exists by condition 1 here. Obviously assuming that F here is a well-ordered aggregate, then F1 is the rest of the aggregate of F. So all of the other elements except for F1. Well, both of these are actually parts of F. So the aggregate F1 and the aggregate F1, they're parts of F. So we have a part of F, F1, assuming that this is not an empty aggregate, then it does actually contain some elements of F. Then it's an aggregate that contains at least one element that is greater in rank than the F1 here. And therefore, by this condition 2, there is going to be another element, F2, such that I can write F1 as F2, and then F2, where F2 is the element of least rank in F1, and therefore I can rewrite this F as f1, f2, f2. And I can keep going in this way, so I could get that f equals f1, f2, f3, f3, where these elements are increasing in rank. So they're not increasing in size or magnitude, but they're increasing in rank. So the aggregate f, in that case, I can think of as a definite succession of elements starting at f1, then the next one is going to be f2, the next one is going to be f3, and on and on and on. That's not to say that that's all that there is here. There might actually be, after this series of elements, this infinite series, they might actually start another series. So this might go on to effectively infinity, but then we've got another set of elements, G1, G2, etc. There's all kinds of behaviours that might occur, so I'm not going to try to give a full account of all of the different behaviours that are likely to occur, but the point here is that there is a definite succession of elements. So between the f1 and the f2 here, there are no other elements. Between f2 and f3, there are no other elements. So this is very different to what we saw with simply ordered aggregates, particularly with the aggregate of rational numbers with their usual order of precedence, where there we've got between any two elements of that aggregate, we've always got a third element. So effectively in between two elements, there's going to be an infinite number of other elements from that aggregate. That's not the case here. We can definitely choose for a given element the next element that immediately follows that element, such that there's nothing in between. And this is going to be an important property for us to take advantage of when it comes to these well-ordered aggregates, as opposed to just merely simply ordered aggregates. We can also extend this notation to aggregates themselves. So if in our aggregate f we've got two parts, m and n, such that every element of the aggregate m is lower in rank than every element n. So m precedes every m of aggregate m precedes every element n of aggregate n. Then we can actually use this notation here between the aggregates to say that m, well, I don't really know how to say it. Maybe m precedes n, or m is lower in rank than n. It doesn't really make any difference, but we can extend the notation. So obviously the notation here has a slightly different meaning than the notation when it's used between elements, but it's got an interpretation that's well understood. Okay, so that's the basic definition of a well-ordered aggregate. So we're going to move on now to just a couple of theorems. I'm going to go through a proof, maybe a couple of proofs, but there's a few important theorems that I just want to explain. So let's have a look at the first theorem from this section. So Theorem 12A. So the 12 is referring to the section in Cantor's work, which is section 12, and A, the first theorem from this particular section. So every part f1 of a well-ordered aggregate f has a least element. I think there are a couple of assumptions that we need to make here. Well, there's at least one assumption, namely that we don't assume that f1 is going to be some kind of empty aggregate. I guess if f1 were an empty aggregate, then it'd be pointless trying to find a least element. F1 certainly wouldn't have a least element. I'm not sure that an empty aggregate would be considered anyway as a well-ordered aggregate or anything like that. So that's going to be kind of an important consideration, that there are definitely elements in this part here. We're going to have to bear in mind the definition of a well-ordered aggregate as well, because we're going to be using both parts of the definition in this proof. So F is a well-ordered aggregate, so it has a least element F1. So that is the first part of the definition of a well-ordered aggregate. Now it might be the case that this element F1 belongs to the part F1. Well, if that's the case, then the element F1 must be the least element of the part F1, because if it wasn't, if there was an element F2, say, that was lower in rank in F1, in the part F1, than the element F1, then remember that F1 is a part of F. So every element of the part F1 can be considered as an element of F as well. But then that the existence of such an F2, which is lower in rank than F1 in the part F1, would mean that this F2 is also an element in F, which is lower in rank than F1, but that would be a contradiction to the minimality of this F1. So in that case, we've got that if the part F1 contains the least element F1 of the aggregate F, then that F1 must also be the least element of the part F1. On the other hand, it might be that the element F1 does not belong to the part F1. Well, in this case, let's have a look. Let's take the aggregate or the totality F primed of all elements of F which are lower in rank than all elements of the aggregate F1, of this part F1. So let's think about the second part of the definition of a well-ordered aggregate. It says that for given any part of a well-ordered aggregate, if the aggregate itself contains elements, at least one element that is greater in rank than all of the elements in that part, then there must be an element that of the original aggregate that immediately follows every element that follows that part, that immediately follows that part of the aggregate. Well, in this case, we've got such an element F primed. So this comes back to assuming that the part F1 is not empty, is not some kind of empty aggregate. Because then we've got our part F primed, but F primed doesn't contain any elements that are in F1. So it's completely separate from it. It's completely separated from F1. So that means then that the aggregate F, remember F1 is a part of F, must contain at least one element that is greater in rank than all of the elements contained in this F primed, and therefore there is an element that immediately follows this F primed. That is this element F primed here. So F primed is an element of F which immediately follows all elements of the part F primed, and it turns out that this F primed must be the least element of our part F1. Because if it's not, then we've got two possible cases. Either there is an element G, which is lower in rank than F primed, and G belongs to F1. But then this would contradict the choice of F primed here. Because remember, the elements of F1 are simultaneously elements of F. So that means that this G must be in F. But we chose F prime to be the least element of F, which immediately follows all elements of F prime. So there's no elements between F primed, the part F primed, and this element F primed. So this G, it can't be there. On the other hand, it might be that we've got a G that actually follows F primed, and that G is actually the least element of F1. well, that would mean then that f primed is actually in our aggregate, or in our part f primed here. Because remember that f primed is all of the elements of f that are lower in rank than all elements of the parts f1. So if g is the least element in f1, then f primed is lower in rank, and therefore it must be in f primed, which is a contradiction, because f primed by definition is not going to be in the part f primed. So neither of these can occur, so therefore f primed must be the least element of f1, and that finishes the proof of this theorem. Okay, so let's move on to the next theorem. I've skipped a couple of theorems. Like I said at the beginning of the video, I'm not intending to go through every single theorem. There's just too many of them from this section of the work. So I'm trying to pick out the ones that are going to be most important and most useful to us. So Theorem 12D, every aggregate G, which is similar to a well-ordered aggregate F, is also well-ordered. So remember, this similarity relates to simply ordered aggregates. Two similar aggregates will have the same ordinal type. So if we've got just any aggregate G, but it happens to be similar to a well-ordered aggregate, so presumably G actually has to be a simply ordered aggregate, but it's similar to a well-ordered aggregate F, then G is also well-ordered. So this idea of well-orderedness, it doesn't depend on necessarily specific aggregates, only the ordinal type of the aggregates. That's what determines whether it's a well-ordered aggregate. It's nothing to do with the specific nature of the elements of that aggregate. Okay, and then we've got Theorem 12.E, which I'm going to go through in a more informal way. So I'm not going to go through the proof of it. I just really want to go through the statement, but in a more informal way. So if we start with a well-ordered aggregate G, then if then to each element of G, so lowercase g, we assign a well-ordered aggregate Fg, so F sub G. We do this for each element of G. We assign to it some, we kind of pair it up with some well-ordered aggregate F sub G. And then what we're going to do is we're going to effectively replace each of these elements, lowercase g in uppercase G, with these aggregates that we've paired them up with. So we're going to form a new aggregate H, which is effectively made up of the FGs, in such a way that if FG1 and FG2 are elements of this aggregate, then FG1 precedes FG2 in H, if and only if FG1 precedes FG2 in FG. So in other words, if both of these actually belong to one of these FGs, one and the same FG, then if they precede one another, if FG1 precedes FG2 in FG, then they also, FG1 precedes FG2 in H. Now obviously the ordering here, they have, they're not the same ordering. This isn't ordering on FG, this isn't ordering on H, but we can define our ordering, at least part of our ordering in H, in terms of the ordering in that's defined on FG. But if the elements FG and FG primed, if they're elements of H, but they're actually in different FGs, then we'll say that Fg precedes Fg primed in H if and only if G precedes G primed in the aggregate, the well-ordered aggregate G. So again, we've got two different orderings here. This is an ordering defined in G, this is an ordering defined in H, but we define this ordering in H in terms of, partly in terms of the ordering in G. And in this case, if we define H in such a way, then H is a well-ordered aggregate. Ordered. And the elements of H are just all of the individual elements of these Fg. So of course there's going to be the assumption here that these Fg don't have any common elements. So this is kind of a union aggregate, really. And this is quite similar to how we, when we did multiplication of ordinal types. And in fact, multiplication of cardinal numbers as well. It's a similar kind of idea. It's a similar kind of idea to that, except here we don't require that all of the Fg are similar or equivalent. So they're just any old well-ordered aggregates. They don't have to be similar or anything like that. So we don't require that Fg be similar to Fg primed or Fg is equivalent to Fg primed. They could have nothing really to do with each other structurally, other than the only similarity being that they're all well-ordered aggregates. We can also say then, in this case, clearly that Fg, so the aggregate Fg precedes or is lower in rank maybe than Fg primed if and only if G precedes G primed in G. Okay, so this is just again something that follows really from the definition here. So that's effectively the statement of Theorem E from this section. I'm not going to go through the proof of it. I think this is going to be sufficient for what we need. We will need this further down the line. So I'm going to move on now to segments of well-ordered aggregates. Let's have a look now at segments and remainders of well-ordered aggregates. So starting with our well-ordered aggregate F, and we choose a particular element, lowercase f, of the aggregate F that is not the least element. Remember, if F is a well-ordered aggregate, then it has a least element, so we just choose any element that is not that one. Then we can define firstly, a part A of our aggregate, which is made up of the elements of F that are lower in rank than the element F. So this element F is not included in this part A, but this particular type of part is what's called a segment. So in this case, a segment of F, or more precisely, we might say the segment of F defined by the element lowercase f. So a segment is a particular type of part. So a part is a much more general notion. The fact that we choose this element to not be the initial or the least element of f guarantees that these segments are not going to be kind of trivial empty aggregates. So there are actually going to be genuinely some elements in there in these segments. And the fact that we don't include f itself guarantees that a segment is never going to be equal, at least, to the original aggregate. We've yet to see if an aggregate can be similar or equivalent to any of its segments. That's something that we're going to be looking at in a second, but at least we can guarantee that a segment is never going to be equal to the original aggregate, because there's always going to be at least one element that's missing, effectively, at least one element. Okay, and we can also define another part to this aggregate, B, and B is made up of, the elements of B are F itself, and all of the elements of the aggregate F which are greater in rank than the element F. So this is what's called a remainder of F, or again we can more precisely say it's the remainder of F determined or defined by the element F. So these are completely separate aggregates within F. They've got no common elements, but not only that, they account for every element also of F. So every element of F will belong to either a segment, this segment, or this remainder. So we can say, for example, that F is the union aggregate of A and B. And since every element of A precedes every element of B, we can also say that A precedes B, or A is of lower rank than B. Again, I don't really know exactly how to say this in words, but the meaning is understood. But we can introduce some new notation. When we talk about segments, we can actually talk about greater than and less than, rather than just some kind of abstract order on the elements. We can actually talk about greater than or less than. So it makes sense that if, for example, we've got two two segments of F, A and A primed, and let's say A is determined by the element F and A primed is determined by the element F primed, and let's also say that F is lower in rank than F primed, then in this case we can say that the segment A is less than the segment A primed. All of the elements of A will also be elements of A primed, so effectively A is going to be an aggregate that is completely contained within this A primed, but A primed will have elements that are not included in this. So this notation makes sense. We can also say, so this applies just to segments. This notation applies only to segments, so this here, whereas this applies to more general parts of an aggregate. This notation here strictly to segments, with one exception. We are able to say that a segment of the aggregate F, for example, so let's say we just choose A, which is a segment, we can say that A is less than F itself. F can't be a segment because that possibility is excluded by this definition here, that we don't include. So if F actually had a greatest element, then the segment defined by that greatest element would not include that greatest element. It might be that segments, our aggregate F doesn't even have a greatest element. That's kind of beside the point. The point is that a segment can never be equal to the aggregate itself. So F cannot be a segment, but we can still say that A is less than F. So this is the one exception to the rule, really. This symbol really just applies to segments, with this one exception. So now let's have a look at some theorems relating to segments. There are quite a lot of theorems in this section now. So this is section 13 in Cantor's book. I'm not going to go through every theorem. I'm not even going to state every theorem necessarily, but I'm going to choose some of them that I think are more interesting. So this is Theorem A from section 13 in Cantor's work. So I'm going to go through this in the statements of this theorem in kind of an informal way. I'm not going to go through the proof of it. and I'm not going to state the theorem exactly as it's presented in Cantor's book, but I am going to go through the statements of the theorem just in an informal way. So we start off with two well-ordered aggregates, f and g, such that f is similar to g. So that means that they can be imaged onto one another. So the meaning of this symbol is that we've got this imaging between this correspondence between f and g called an imaging. And okay, so what I'm going to do now is I'm going to just kind of diagrammatically represent f and g. So this is not to suggest that f and g are finite things or anything like that, but it's just to kind of illustrate what the theorem is saying. What I'm going to do is I'm going to take an element f of the aggregate f, and I'm going to take the segment that corresponds to that element, and that's going to be a. So what the theorem says is that to every segment of segment A of f, there is a segment B of g that corresponds to it. So every segment of g is determined by some element g, and let's say that this is the segment B of g. Well, this segment corresponds, this segment of f corresponds to this segment of g, and also vice versa. So it's like a one-to-one correspondence between the segments of f and the segments of g. Not only that, the segment A of f is similar to the segment B of g, and moreover, the element f that determines the segment A and the element g that determines the segment B in g, these will correspond in our original imaging. So remember, because f and g are similar, we've got this imaging, this one-to-one correspondence that preserves the ordering of the elements in their respective aggregates. Well, under this imaging, then element f must correspond to element g, and vice versa. So remember, it's a one-to-one correspondence. So not only do we have a one-to-one correspondence between elements, we've also effectively got a one-to-one correspondence between the segments of the two aggregates as well. So that's Theorem A. I'm not going to go through the proof of it. I'm going to move on to Theorem B, which I am going to go through the proof of Theorem B. So let's have a look at Theorem B from this section, which says that a well-ordered aggregate f is not similar to any of its segments A. So there's a very clear difference in behaviour between segments, between the relationship between a segment and the aggregate, and part and the aggregate. So a well-ordered aggregate could quite easily be similar to one of its parts. And this is not unusual to observe this. It wouldn't take long to come up with an example where you've got a well-ordered aggregate that is similar to one of its parts. But on the other hand, a well-ordered aggregate cannot be similar to any of its segments. So segments are a particular type of part, but they've got very different behaviours. So we're going to go through a contradiction here. So we're going to start out by assuming that we can actually find a segment A of f such that f is similar to A. And bearing in mind what this means, that f is similar to A, that means that there's a one-to-one correspondence between the elements of f and the elements of A that preserves that the ordering on the elements. So I'm going to need to consider here A as, on the one hand, a segment of f, and on the other hand, as an aggregate in its own right. So if I consider A as a segment of F, then using Theorem A, that I've just, I didn't prove it, but I went through the statement quite kind of informally. Because F is similar to A and A is a segment of F, that means that there must be an A primed, which is a segment of A, such that A is similar to A prime. So this correspondence between A and A prime is guaranteed by Theorem A that I proved a few minutes ago in this video. It also follows, obviously, that A primed is similar to F as well. Well, I need to play the same game now. If I consider A primed as a segment of A and also A primed as an aggregate in its own right, then I can find A prime primed, which is a segment of A primed, that corresponds to A primed. So again, that's guaranteed by Theorem A that we looked at a few minutes ago, because A is similar to A primed. So the theorem applies. And I can continue this process, so I can find more and more segments. Note also that A prime primed is similar to A primed, and therefore A prime primed is similar to F. So what I get is effectively a sequence of segments, starting with A, and A will be greater than A primed. Now, this has to be the case because through the definition of segment, we know that a segment of a well-ordered aggregate cannot be equal to the aggregate itself. There's always going to be fewer elements in the segment than there are in the original aggregate, because the element that defines the segment is never in the segment itself. So we can always say that the aggregate that we started with is going to be greater than the segment. So we know that A is going to be greater than A primed. A primed, remember, has the segment A prime primed, so A primed is going to be greater than A prime primed, and this continues. So A new, which is greater than, etc. Okay, and the elements that define these aggregates, so if aggregate, this segment A is defined by the element F of F, then A primed is going to be defined by the element F primed. A prime primed is defined by the element F prime primed. These are all elements of F, so they can be compared, put in an order, and we can say that F is going to follow F primed. F primed is going to follow F prime primed, etc. So note here that even though they look kind of similar, these are different symbols, they're representing different things. But we get an infinite descending chain of elements here. And these elements themselves, if I stick them into an aggregate, are going to form a part of F, the well-ordered aggregate F. So we've also seen that any part of a well-ordered aggregate has a least element. Well, that's not what we're seeing here. We've got a part of F which is made up of these elements here, but they form a descending chain of elements, and none of these are going to be equal to each other because they're all defining different segments. If any of them were equal, then they would define the same segment. So it's an infinite descending chain. There's obviously no least element there. So that contradicts the theorem that we proved earlier, that every part of a well-ordered aggregate has a least element. So therefore, this cannot be possible. So we've got our contradiction. So therefore, a well-ordered aggregate is not similar to any of its segments A, and that finishes the proof. So I'm just going to wrap up this particular video, with just a few more theorems from this section. So Theorem C, a well-ordered aggregate F is similar to no part of any one of its aggregates A. So this is very similar to the theorem that I've just gone through, Theorem B, although rather than talking about segments of the aggregate, it's talking about parts of segments. And the proof of this goes in a very similar direction to the proof of Theorem B. So I'm not going to go through the proof of this. It's very, very similar. It leads to pretty much the same contradiction. You form a part of the aggregate F that doesn't have a least element, which is a contradiction to Theorem A from section 12. Theorem 13D, two different segments A and A primed of a well-ordered aggregate are not similar. Okay, something that I didn't make as clear earlier as maybe I should have done is that any two segments of an aggregate stand in exactly one relation to each other from amongst the three possible relations. A is less than A primed, A is equal to A primed, or A is greater than A primed. So if the two segments are different, then they're not equal, so we're either in this case or this case. So let's assume we're in this case, in which case, rather than considering A and A primed as aggregates, as segments of some aggregate F, if I now consider A as a segment of the aggregate A primed considered as an aggregate in its own right, then we fall back to Theorem B, that an aggregate, a well-ordered aggregate, cannot be similar to any of its segments. So that means that A, being a segment of the well-ordered aggregate A primed, cannot be similar to A primed. And Theorem 13E, two similar well-ordered aggregates F and G can be imaged onto one another in a single manner. So again, I'm not going to prove this one. I don't want to get bogged down with proofs here. I'm really wanting to just pick out the essential bits that we need to move on to the more interesting stuff, at least on ordinal numbers, which is coming up, which I'm going to make a start on in the next video. There is another theorem, so I'm going to skip a few theorems here, so FG, but there is a theorem 13.n, which I'm not going to state here. I'm actually going to leave that to the next video and include it in the next section. So it's a slight change in the order in presentation from the book, from Cantor's book. It's just, I feel it fits a little bit better with the next section. So I'm going to leave that one out. So that's the end of this video. Next video we're going to be moving on to ordinal numbers, which I think is really the main focus of this second article. So I want to thank you for watching this video, and I look forward to seeing you in the next video.